Welcome to this video lecture on acceptance sampling. Acceptance sampling is a way of determining if batches from a process should be accepted. Now, instead of using sampling inspection, it would be better to use right first time, manufacturing products right first time rather than inspecting afterwards to see if the products are defective or otherwise. But sometimes it's inevitable that some defective units will be made. And if that's the case, the next best thing to do is to use effective 100% inspection to identify and remove all of the defectives. But that may be too costly or otherwise not possible. And so in those cases, sampling inspection can be used to ensure that the level of defectives is not above some specified threshold. So acceptance sampling is carried out by following a sampling plan. And a sampling plan consists of a rule for taking the sample and a rule for making the decision based on the sample. So this sampling plan, n equals 8, acceptance number is 1, rejection number is 2, calls for a sample of 8 units to be randomly selected from throughout the entire batch. And then if one or fewer defectives are found in the sample, then the rest of the batch is accepted. If 2 or more defectives are found in the sample, then the entire batch is rejected. And if a batch is rejected, that batch undergoes rectification, which means that it is subjected to 100% inspection with replacement of every defective unit with a non-defective unit. So a batch which is rejected actually leaves the inspection station 100% conforming. Now, whether or not any particular batch will be accepted depends partly on the quality of the batch itself, but also partly on the sample which happens to be drawn from the batch. So it partly depends on the look of the draw. So it's not certain what will happen with sampling inspection because samples will differ. So we define the incoming quality of a batch, the incoming quality level, that's defined by P. It's the proportion of defectives in the batch. The incoming quality level. And depending on the incoming quality level, there's a certain probability of acceptance of a batch like that. And that's denoted as capital P subscript A. So the acceptable quality level is the highest acceptable process average percent defective. So suppose, for example, that 5% defective is considered good. Well, then we're saying that 5% defective as an average for the process is acceptable to us. And batches that come from a process like that should be accepted. The other measure we have is rejectable quality level, RQL, very often called LTPD, the lot quality percent defective. This is the level of defectives which is not acceptable, not even in a single batch. So let's say 40% is the LTPD. So notice now that the AQL, the acceptable quality level, refers to the level that is acceptable in the process, whereas the LTPD refers to the level which is not acceptable even in a single batch. So with these values, suppose we have an AQL of 5% and we use the sampling plan that has just been described, n equals 8, accept 1, reject 2. The probability of acceptance of a batch from a process with an AQL of 5%, the probability of acceptance is 94%. 94% of batches that come from a process with 5% defective are accepted. And of course they should be accepted because 5% defective is acceptable. The other 6%, 100% minus 94%, are rejected just because they are unfortunate. These batches come from a similar process, but the sample that was drawn just happens to contain 2 or more defectives. So there is a small probability of rejecting a good batch, and that's called the producer's risk. For batches that come from a process where the incoming quality is 40%, that's the LTPD, the lot tolerance percent defective, or the rejectable quality level. These batches should be rejected because that's not acceptable, and most of them are rejected. 89% are rejected, leaving only 11% accepted. Those 11% are accepted because even though the batches are poor, the sample of 8 units on those occasions happen to contain 1 or fewer defectives. So that 11% is the consumer's risk, beta. So sampling plans can do a few things for us. Sampling plans can identify a very bad batch immediately. A batch which has an incoming quality worse than the LTPD is almost certain to be rejected. And the second thing that sampling plans can do is identify an unacceptable process sooner or later. If batches are repeatedly presented from a process which has an incoming quality level worse than the AQL, then eventually some of the batches will get caught by the sampling process, and that process will be identified as non-conforming. One thing that sampling plans cannot do for us is guarantee a correct decision in any one case. We cannot be certain that the decision made on any single batch is the correct decision because we're basing our decision on a sample, not on a census of all of the items in that batch. So if we draw a graph of the incoming quality level on the horizontal axis against the probability of acceptance on the vertical axis, we get an operating characteristic curve. This shows us the level of protection that the sampling plan offers against any value of the incoming quality level. So we've already talked about an incoming quality level of 5%, and we can see here that the probability of acceptance is very high, and it should be high because that's the AQL. We've already talked about an incoming quality level of 40%. We can see here the probability of acceptance is low, and of course it should be low because that's rejectable. But if we talk about an incoming quality level, let's say about 20%, we see from this graph that the probability of acceptance is about 50%. We call that the indifferent quality level. So this sampling plan would not be useful for protecting against an LTPD of 20% because a batch like that is just as likely to be accepted as rejected. The average outgoing quality downstream from inspection will be better than the level of incoming quality because rejected batches are removed and rectified, and any unit found in an accepted batch, any defective unit that happens to be found during sampling is replaced. Now, if the incoming quality is very good, well, of course, the outgoing quality will also be very good because the batches won't get any worse as a result of being inspected. And if the incoming quality is very bad, the outgoing quality will also be very good because there will be many rejected batches and those will all be rectified so that they will be 100% conforming when they leave the inspection station. So there is some unhappy medium where the average outgoing quality is the worst that it can be. And this AOQL provides a worst case guarantee for the average outgoing quality for a continuous series of batches from a stable process if we have rectification in place. Instead of using single sampling plans, we can use double sampling plans. So instead of taking just one sample and making a decision, we take 2 smaller samples. The first smaller sample is taken, and if the results in that smaller sample are very good or very bad, then we accept or reject that batch straight away. But if it's not certain what decision should be made, then we go ahead and take the second sample in the double sampling plan. And the advantage of this is that on average, the sample sizes will be smaller, and so it saves resources. We can extend this to multiple sampling plans where 7 subsamples can be taken. And after each subsample is taken, a decision can be made to either accept the batch at that point or reject the batch at that point or proceed to take the next subsample. And sequential sampling takes this concept to the limit. After every unit of product is selected and inspected, a decision is made at that point to either accept the batch now or reject the batch now or select one more unit of product. Some practical guidelines for sampling plans is that in order to find a suitable sampling plan, the first thing you need to do is to identify an AQL and an RQL. Again, the AQL is the acceptable quality level from the process in the long run. The RQL is the unacceptable level of quality even for a single batch. Larger values of the RQL to AQL ratio tend to lead to smaller samples. So if you have a choice, if you have an AQL and you have a choice about setting the RQL, if you can set a large value, it will provide you with typically smaller sample sizes. Sometimes you can choose the batch size because you might have a more or less continuous process where there aren't predefined batches. If you can choose the batch size, there are a couple of things to keep in mind. If you choose large batches, then fewer samples will be needed because only one sample is required per batch. However, if you reject a batch, then there is a large batch which requires rectification. And make sure that whether you're using single sampling plans, double sampling plans, or multiple sampling plans, all samples are drawn randomly from the entire batch. Resist the temptation to take samples at the start of the batch because always the sample must speak on behalf of the entire batch. So every sample should be drawn randomly from across the entire batch. You can read more about this in the textbook in section 8C.